this meeting. It's a pleasure to introduce Preetum Nakkiran from UCSD, who will be talking about is overfitting is actually benign.
Right, thank you. So this is not going to be an actual talk. It's going to be sort of a progress report on a project that's in progress. So I'll discuss some motivations, show some plots, and pose some open questions that I think we have something about solving. This is going to be joint work with a number of people. So Neil and Amir at UCSD, who are here too, Gil at MIT, others joint work with Yamini at Harvard, and of course with Nakkiran, and maybe with you. Okay, so first here's a teaser. We've all seen this experiment, right? Let me walk through this quickly. So the experiment here is, let's train some networks on CFAR. So D naught is the original CFAR distribution. And what we're going to do is train on DP, where DP is a noisy version of CFAR, where with probability P, we have a uniformly random label. Okay. Now, as we vary P, we're going to do the following. We'll train a network to interpolation on samples from the noisy distribution, and then evaluate test error on the clean distribution, D naught. And you've seen this plot, this paper here. So what happens is, as we vary the label corruption P, and look at how networks perform on clean labels, and we see the following thing, where increasing amount of label noise in the train set shows up as errors at test time. And this plot is usually shown as evidence of some kind of benign overfitting. Right? These are cases where interpolating noise on the train set does not somehow hurt you too much. But it does hurt you, right? Note that you are incurring more test error when you train on noisy distributions. And in particular, for higher noise rates, you're far from base optimal. So the base optimal classifier in the setting would just be this flat line down here. For any noise level besides 100% noise, as long as you have some signal, the base optimal classifier will recover that signal. So the question here is, for this finite sample setting, we're seeing that noise does actually hurt. And what happens? Yeah. Please interrupt, like whenever. Yes.
So you say it's a horizontal line of 0.1, or tells you that the base optimal is not 0.01.
Oh yeah. Oh, you're saying this distribution itself might be noisy. Is that what you're saying? Sure. Yeah. Fair. So.
Or you might not be able to.
What do you mean you might not be able to?
Yeah, the point that you see there at 0.1 might not be the optimal.
Oh, sorry. Yeah, I mean, base up like if there was no base risk here, then this would just be flat at 0 as base optimal. I'll show a much simpler setting so we can actually understand what the base optimal classifier is. This is sort of motivation. But the question really is, okay, this is a finite n. What would happen to this plot as you increase n? Will these lines get closer and closer to base optimal, or will there always be some lower bound of the effect of noise? Will noise always hurt you? Okay, so we've actually done experiments similar to we've done and the question is, like, do these points, will they at least converge to what we know is the epitaph, right? But you can phrase this. We have simpler settings so we can understand it better. So by the way, notice that your better and better networks seem to be getting closer and closer to this line here. And in fact, that does seem to be happening. There's other paper which, among other things, shows that for very good networks, you have this effect that training on P% noisy inputs on the train set will produce a classifier with roughly P% noisy outputs. And this is true even for structured forms of label noise. And it seems to be true even for varying n. This is sort of independent of. For any large enough n, as long as you interpolate, you see the effect. This paper studies generalizations of this phenomenon. I won't discuss that here, but in this project, we're going to study the consistency implications of this statement and try to simplify this setting as much as possible to try to understand what's going on here. Okay. Yeah, and also, please interrupt me. There's no real plan here. Okay, so let me define what I mean by consistency, and then we'll discuss the experiments. So we have some distribution D on inputs X labels Y. We have some models that map inputs to labels, and we have some notion of a loss function on models. So this could be in the regression setting, this will be the mean squared error. In the classification setting, the 0-1 loss. And given the loss in a distribution, we have this notion of the optimal loss, which is just the best loss that's achievable for the distribution. Okay. Now, what is a learning method? A learning algorithm is a sequence of algorithms indexed by sample size. And each algorithm takes in n samples and spits out a model. So allowing learning algorithms to be non-uniform in that they do different things for different sizes of samples, which you often want, like in the non-parametric case, you would change your bandwidth according to the sample size and things like this, just generically. Okay, so with this setup, what is consistency? We say a learning method is consistent for a given distribution with respect to a given loss if in the limit in the asymptotic limit of samples, the learning method converges to the optimal loss. Okay, so this is consistency. Note in particular, we're not changing the problem, right? Like the dimension of the problem is staying the same. The only thing that's changing is the number of samples. There's consistency for a fixed problem. So in particular, we say it's consistent if asymptotically the algorithms converge to the optimal loss. Okay, good. And now the question we ask is, are modern learning methods consistent? Are modern interpolating learning methods consistent? So to ask this question, I have to define what I mean by a modern learning method. Roughly, we want to be considering a sequence of algorithms that correspond to training networks of increasing size. So you want to grow the size of the network with the size of the data. There are two natural ways to do this, roughly. There's the over-parameterized limit, where you do this while keeping the network size always bigger than the data size and training to interpolation. And then there's the under-parameterized limit, where you grow the size of the network, but always slower than the size of the data. And this is sort of the classical limit. And I claim that these two limits have different behavior. In particular, the under-parameterized limit is often consistent. Like it's easy to formulate versions of to formulate the statement in ways that you can show it to be consistent, sort of for classical reasons, right? If the data is large enough, as long as your model family is growing in expressivity, you will reach consistency. And there are proofs of this in various settings. Mathis, Talgarsky, Joeli, and Justin have this early stop networks are consistent paper recently, which proves some version of this. But this should be the classical limit. The over-parameterized limit is what we want to study now, which is here, and I claim that there's evidence that this is inconsistent in sort of almost all reasonable settings. Clearly not all of them, right? Because we know it's possible to interpolate and be consistent. But somehow there's a wide variety, like in practice, if you to actually train networks, they seem inconsistent. Now, okay, let me show a very simple, yeah. Yeah. Which one of the options? So yeah, so the bottom one. Yeah. So okay, yeah.
I think we had this conversation before, but
Yeah.
I'm not sure we know that.
Yeah. So I claim like I can formulate this in sort of a reasonable way and sort of prove it. Like Mathis' paper proves some version of this.
Size would be larger.
Sorry?
The size never should be larger. Doesn't sample size. It's just
Yeah, exactly. Yeah. So the under-parameter limit is really meant to capture this thing when you don't overfit, like when the train error is close to your test error. So you can instantiate this limit as saying like you can also do the one epoch training. Like if you just train for one epoch, then you should also get consistency. But yeah, basically the under-parameter limit should be cases when the train error is close to the test error. You have normal sort of generalization bounds, and optimizing on the train set is exactly what you want. There are various ways to formalize.
Model, it's easy to prove something like that, but if you have a real neural network, how do you know you're not converting to a local mean?
Yeah, I agree. Yeah, this could be trickier and even not known for deeper networks. If you allow yourself infinite optimization time, then you can make this. I mean, yeah. No, but I think like morally this is true, and like the question is how far can we prove that it's true is a different question.
think a more precise maybe way to say it is to say that if you can optimize it, if you can find the global minimum, that's it.
Yeah, that's definitely true. That's definitely true. Yeah. Yeah. But I want to study this one now, which I claim the mini-statistic setting was inconsistent. So let's try to simplify the setting as much as possible to understand the behavior. So here's a very simple distribution. The current distribution on X and Y. X is some normal Gaussian in some dimension, 100 dimensions. Y is independent of X and just a plus minus 1 bit with some bias. It can even be unbiased. Okay, now consider solving the regression problem in this setting. So the optimal regression function is just a constant function. It's the bias of the bit. For example, if the bias is 0, the optimal function is just the actual 0 function. Now we ask, what happens if we try to solve this regression problem with deep learning? Right? We take some neural network and we train it to interpolation on samples from the distribution. Do we learn the 0 function? Do we learn the constant function? And if you do this experiment, there are lots of design choices here, right? Like you have to choose what kind of MLP or all the design choices. But I claim like if you try to do it for almost all reasonable hybrid parameters, you will not see consistency. So here, as you increase the size of the samples and look at the excess width, the excess width does not convert to 0. There's much more samples you think to interpolation. Okay. So briefly, yeah, here's a good question. So briefly, consider this setting. You're solving regression in a very simple case. X is a normal Gaussian in 100 dimensions. Y is independent of X and a biased bit. And you want to solve the regression problem in this case. The optimal function is constant. The question is, if you train an MLP to interpolation, do you learn the constant function? And I claim that if you actually try this, so any actual instantiation of an MLP that you train to interpolation, you will not learn the constant function. You will not even convert to the constant. Yeah. Oh yeah. So I think Neil or Neil founded this one. This is like a 3-layer.
That's a
3 by
3-layer,
5
512 with
3 by 5
100-dimensional Gaussian.
Yeah, and this also holds for like one layer by 512.
One layer, 10,000.
So what is these 100?
These 100 here. This also holds with these like with 10 1,000. Yeah, it doesn't matter.
And you put a 3-layer network,
Mhm.
500.
Yeah, but those details don't matter. So we've changed the width, we've changed the depth, we've changed the initialization scale. As long as you interpolate, I claim you're not going to get this consistency. If anyone breaks this, if anyone can break this, like show me some natural training that will be consistent, I'll be very interested. We haven't found it. Yeah. Is it what? It's not important that it's biased. This will be for the next slide. It's not. This works with the. In fact, this experiment
for unbiased and biased.
Yeah. This experiment with the bias.
This is with a 0.7 bias, but we have
Yeah.
like 0.5 and 0 and all.
In fact,
it's the same thing.
Yeah, I'll show you. Actually, we have the next slide. Yeah. So here we. So right. So this is not a problem, right? If you stop after one epoch, then you're going to be consistent easily. This is like a one epoch version of this. If you don't interpolate, very easy. You can learn the constant function. It should be obvious. Yeah.
Is it an issue of, you can tell us how many samples? I mean, presumably you.
In terms of precision. So what I'm studying is, because I want to study consistency. I want to study, is this method consistent as I send samples
Right,
to the
right.
student?
Okay, so you don't think it's an issue of just having, I don't know what the.
Absolutely not. I mean, we've done like 20K samples. We've even scaled this up to like,
We went up to 100. 200.
yeah. I mean, you learn the constant function. You only 20K samples, right? But like, yeah. The question is, yeah, we want to know the asymptotic behavior of this line as n goes to infinity. Yeah. Any other questions?
What, maybe you're gonna make what the talk about, but how does this function look like? Is it learned? Is it just?
Okay, good. Yeah, perfect. Perfect. Yeah. So let's look. It's easier to understand the classification setting. So train on the exact same thing, exact same distribution, but now you care about the classification loss. do the exact same thing, just measure the classification 0, 1 error. So now the optimal function, you have p bias. On the y, the optimal function is just the one function, right? For the classification loss, train and MLP, same thing. Look at how, as you vary the p, as you vary the train distribution, as you vary the bias of the input, how does the bias of the output change? Right? You understand the setting? So this is changing the training distribution, the bias of y, and this is looking at the bias of f. So the optimal thing here, the base optimal thing is the step function. Right? Any bias less than half, the optimal function is 0. Any bias more than half, the optimal function is 1.
What's the training loss?
This experiment was with MSC, but this works for cost entropy too. My previous paper on distribution.
I see that what is
Yeah.
With MSC. No. So there's two questions, right? Like, no. So you have to fix a training method. You can train with whatever loss you want. Then you have to like the loss used at train time and the loss used at test time are always different. Right?
No, but if you train with the expected square loss, the expected which based on the expected square loss.
Sure. But the base optimal with respect to square, it's the same. It's just no. If you take the sign, right? So okay. So the base look like if your bias is positive, the base optimal with the square loss is mu, which is positive. You take the sign as mu, you get 1, and that's optimal. That's the base optimal classification function. Right?
So the other vector nulli, to subtract p, this is less than sign of p, right?
If you have a no, but so what I'm comparing here is which plot are you talking about?
When you say interpolate here,
Yeah.
You didn't just interpolate in the sense you get the correct signs for everything.
No. Fit the actual loss. Yeah, fit the actual loss.
Okay, the actual loss being squared loss.
Yes. Yes.
And so, yeah, this is it's a bit strange to then in test time test the additional loss.
But you always do this, right? You you never actually train the 0, 1.
I think you have to be
That's what you always do, right? You always you train with cost entropy, you care about 0, 1, you train with MSE, even you care about 0, 1. Like you can't train on 0, 1, right? It's not a
Yeah, but you cannot, it's fine, but then you shouldn't say ideally what you should get is sine of p, right? I mean, or sine of p minus 1/2. Right? Ideally, what you should obtain is p.
So the raw values will be p, but how do you obtain a classifier out of the function that you get? You threshold it, and then you'll get 0. You get plus or minus 1, right? Like when you take the argmax when you train a network, right?
Sure.
And that's what we're measuring. Yeah. So we train it as a regressor, then we threshold the function and use it as a classifier, which is what we do, right?
So what you're showing here, I see. So if we say if of x, it's really
Sine of f of x. Yes. But that's yeah. I mean, this is implicitly like what you do when you use regression for classification, right? You take the argmax of the regressor. This is what you're doing. Yeah. So this is to your previous question, which is as you change the bias of the input. Like this is telling you about the structure of the function. Like what function do you actually get? And the point is that you're getting something that is very close to this line that the noise level at the outputs is close to the noise level of the inputs. This statement is in general generalized in my previous paper on distributional generalization, but the point for our experiments is that this behavior does not change as you scale up the samples. So in particular, as you scale up the samples here from the 128 to 20K, you're not getting closer to base optimal. The interpolating network is inconsistent in this sense. Okay, let me speed up. So yeah, there's an iteration. So yeah, let me just skip this. Okay. So here's the status of this project and open questions that are allowed to address. We have some sort of negative observations and the positive. The negative, there are many settings where interpolating methods are inconsistent. On the positive side, so in the regression setting, you can write risk as bias plus variance. And you can ask if you're inconsistent or inconsistent because of the bias or because of the variance. And there's empirical evidence that neural networks are asymptotically unbiased. Okay, so the bias is right, but you're inconsistent because the variance does not go to 0. I think the statement that networks are asymptotically unbiased is already interesting, and it would be nice to prove it. Like I think there's a sort of a statement that if it's true, it's sufficiently strong that we might be able to prove it. But I don't know how to do it. What's the statement? But unbiased in the sense that, in the classical sense, of like, is it pointwise unbiased? As a regressor, is the over the training procedure. So this is like in the bias sense of like this in statistical bias.
Over the training data.
Training data and any randomness in the training procedure itself.
For example, can you claim essentially that they behave like one nearest neighbor?
Yes, okay. One nearest neighbors also has behavior that's asymptotically unbiased, but non-decreasing variant, and in particular, it would have these kinds of plots that we expect. Yeah. It would, in particular, it would have this exact relation between input bias and output bias. Yeah, so was the asymptotic unbiasedness claim clear? Sorry. Yeah, so like pointwise, you're getting the right bias, you're just not getting vanishing variance. Yeah, so there's a negative, that's a positive. What's interesting here is we have a lot of theoretical settings where overfitting is benign, right? Where we know interpolators can be consistent under some assumptions. On the other hand, we have a lot of experiments where that seem also natural, but interpolating does not appear consistent. So the question is sort of what is the gap? Can we understand which of these assumptions break down, and can this guide us towards maybe more realistic assumptions that capture these settings? Why is overfitting benign in theory but not benign in practice is the question. And then another thing is like, can we prove this asymptotic unbiasedness? Here's a very clean theory open question that I think can make progress. But maybe I think people in this room probably have the tools to answer this question. Consider just the same setting. X is Gaussian, Y is also Gaussian, independent of X. You use an RBF kernel. You interpolate with an RBF kernel or with a Laplace kernel, right? Now, for what choices of bandwidth is the RBF kernel consistent? So if we consider the interpolating method as training an RBF kernel to interpolation, right, with a particular bandwidth choice, can we understand for which choice of bandwidth the RBF kernel is consistent or inconsistent? And is there any choice that makes it consistent? So like it's really simple setting, right? Like there's no label structure, everything is Gaussian. I feel like we should be able to understand it. Maybe someone has the tools to understand it.
Do you have a reason empirically safe? Or like for some choices it is and some it isn't?
We're trying, yeah.
Something you just showed that there is.
Sorry?
Do you know that something is consistent?
I think we haven't found a setting that is consistent yet, although it's maybe murky. Like we haven't completely figured this out yet.
There are some that look like they're consistent as the bandwidth is increasing. There's certain bandwidth that seem to show some inconsistency. It needs to be explored.
Yeah, it's not clear.
The direction of consistency, there is a lot of the positive direction.
Even that, I don't know. I haven't actually seen like yeah, but you can't scale the problem size. You don't want to scale the dimension with the samples. You want to like. I haven't seen any results even for positive results yet. Yeah, everything is fixed. You only scale n. Yeah. But I haven't actually seen any results to tell me about this setting.
When you say RBF kernel regression, the number of kernels goes to infinity also.
The number of what?
The number of kernels, the number of bumps, number of.
Data points. Yeah. There's only one thing that changes. It's the size of the training set.
But then it's inconsistent for any topic, it's inconsistent. The result of for any output.
Oh yeah, that doesn't need to be fixed. You're allowed to change the bandwidth of the dimension.
But there is, for example, this is one case.
Yeah. That is, yes, that is, yeah.
But this is for Gaussian. Maybe there's another kernel.
Right, sure. Just to say
Yeah, maybe, but basically, like I think understanding this better might tell us more about why it's happening a lot in practice or not. Yeah. Okay, I am very much over time, so thank you, and send me an email if you solve any of the problems.
So I just, I'm a bit confused. I'm sorry. It's the beginning, but anyway, a few years ago, Misha tells us that population and engagement system neural networks, and now it's not.
I don't know how to
What's so it seems that something is different, right? Like, so, I mean, but I don't know if I can formulate it, but what is it that like, what do you feel is fundamental? Like, what's the first experiments you did a few years ago?
It's not, we can maybe discuss later, but there are some, like if you use, for example, fractional power kernels or something. But if you use Gaussian kernel, and then you will have to integrate much less.
Where does the kernel come in? You just use a neural net? You just train the neural net, right?
The neural net is fully connected, looks very similar something to Gaussian kernel in the process.
Do you think the issue is that the network? I'm just trying to understand. Do you think the issue is network architecture?
I don't think so. It's not network architecture because it is an MLP, but the initial experiments were with ResNet on CIFAR, like adding label noise. We haven't found a network architecture that makes sense consistent. I think it's like very, yeah, I don't know about, yeah.
Yeah.